Hi guys, this is the part 2 of real numbers. Okay, let's begin from here where we stop in the at the last class, irrational numbers. Let us take a look at the number line again. Are we able to represent all the numbers on the number line? The fact that there are infinite numbers left on the number line, right? To understand it, to understand this, consider the equations: x square equal to 4, 3x equal to 4, x square equal to 2. From equation 1, we know the value of x for this equation are 2 and minus 2. We can plot 2 and minus 2 on the number line. 3x by 4, 3x equal to 4, x is 4 by 3. That also we can plot on the number line. X square equal to 2, x is plus or minus root 2. Consider x equal to root 2 for example. Can we represent root 2 on the number line? What is the value of root 2? To which the number does root 2 belong? Yeah, we can do by using long division method. This number is repeating. See, here it is not stopping anywhere. The number of decimal points they have been increasing, not with a without a particular pattern. Okay, 4142 135 and so on. If you go on finding the value of root 2, you will observe this. Okay, is neither terminating nor repeating decimal. So far we have observed that decimal number is neither terminating nor repeating non-repeating decimal. So far we observed either terminating or non-terminating repeating decimal, which can be expressed in p by q form. So these are known as rational number. Any number which can be represented in this form p by q, that is termed as rational number. But the decimal number root 2 is not non-terminating and non-recurring decimal. Can you represent with this using bar? No, we can't. These type of numbers are called irrational numbers and they can't be represented in p by q form. That is root 2 not equal to p by q for any integer p and q where q is not equal to 0. Similarly root 3, similarly root 5. These are non-terminating and non-recurring decimals. These are known as irrational numbers and is denoted by s or q bar. Okay, so whichever doesn't belong to q, they belong to q bar. Okay, examples of irrational numbers. These are some examples. In 5th century BC, Pythagoreans in Greece, the followers of the famous mathematician and philosopher Pythagoras, were the first to discover the numbers which are not rationals. These numbers are called irrational numbers. The Pythagoreans proved that root 2 is irrational number. Later, Theodorus of Cyrene showed that root 3, root 5, root 6, root 10, root 11, root 12, root 13, root 14, root 15 and root 17 are irrational numbers. There is a reference of irrationals in calculations of square roots in Sulava Sutra 800 BC. Okay. Observe the following table. If n is a natural number other than a perfect square, then root n is an irrational number. Okay. Right? Got it? Now you can classify the numbers in the tables rational, irrational like this. These are rational, these are irrational. Kruti said root 2 can be written as root 2 by 1, which is p by q form. So root 2 is a rational number. Do you agree with this argument? No. Why? See, it should be in p by q form where p and q are integers. Okay. Root 2 is not an integer. Know about pi. Pi is defined as the ratio of the circumference of the circle to its diameter. Pi equal to c by d. C is circumference, d is diameter of a circle. As pi is in the form of ratio, this seems to contradict the fact that pi is irrational. The circumference c and the diameter d of circle are incommensurable. These does not exist. Sorry. That is, there does not exist a common unit to measure that allows us to measure both numerator and denominator. If you measure accurately, then at least either c or d is rational. Okay, so pi is regarded as irrational. The Greek genius Archimedes was the first to compute the value of pi. He showed the value of pi lies between 3.140845 to 3.142857. Okay, Aryabhatta, the great Indian mathematician and astronomer, found the value of pi correctly up to 4 decimal places, 1.41116. Using high-speed computers and advanced algorithms, pi has been computed to over 1.24 trillion decimal places. Okay, this is the expansion. Okay, the decimal expansion of pi is non-terminating, non-recurring, so pi is a irrational number. Note that we often take 22 by 7 as an approximate value of pi, but pi is not equal to 22 by 7. We celebrate March 14th as the pi day since it is 3.14. Okay, so 3 is March, 14 is date. Okay, what a coincidence. Albert Einstein was born on March 14th, 1879. Find the value of root 3 up to 6 decimals. That you can do by using our division method. Okay, representing irrational numbers on number lines. This is quite interesting. We have learned that there exists a rational number between any two rational numbers. Therefore, when two rational numbers are represented by points on number line, we can use a point to represent a rational number between them. So there are infinitely many points representing rational numbers. It seems that the number line is consisting of points which represent rational numbers only. Is it true? Can't you represent root 2 on number line? Let us discuss and locate irrational numbers such as root 2, root 3 on the number line. Locating root 2 on number line. Draw a unit square OABC. This is unit square on the number line with each side is 1. Okay. According to Pythagoras theorem, the diagonal OB is nothing but side square plus opposite side, adjacent side square plus opposite side square under root over 1 square plus 1 square, that is root 2. Okay, we have seen that OB equal to root 2 using compass with O as the center and radius as OB. Draw a line draw an arc on the number line. That arc represents which corresponds to K. OK represents root 2. Okay, locate root 3 on the number line. How to locate root 2 on the number line? This is root 2. From here, draw BD perpendicularly extending 1 centimeter. Okay, perpendicular to line OB. Then this line OD represents root 3 using Pythagoras theorem. Okay, root over root 2 square plus 1 square, that is root 3. Using a compass with center as O and radius as OD, draw an arc which intersects the number line at line L. This OL represents root 3. Not a very big deal, right? So from this we can conclude that many points on the number line can be represented by irrational numbers also. In the same way, we can locate root 10 for any positive number integers n after root minus n minus 1 has been located. Okay, this you can locate on the number line using this. Okay, 2 and 1. After 2, extend this is 2, extend 1 centimeter up, okay, vertically, and draw the line meeting the end points from O. Okay, then that is nothing but root 5. Okay, right. Real numbers. All rational numbers can be written in the form of p by q, where p and q are integers, q not equal to 0. There are also other numbers that cannot be written in the form of p by q, where p and q are integers and are called irrational numbers. If we represent all rational numbers and all irrational numbers and put these on the number line, would there be any point on the number line that is not covered? The answer is no. The collection of all rational and irrational numbers completely covers the line. This combination makes a new collection called real numbers. Okay, that is what we are discussing, real numbers. Okay, we can say that every real number is represented by a unique point on the number line. Also, every point on the number line represents a unique real number. So we call this as the real number line. Here are some examples of real numbers. We may find that both rational and irrational numbers are included in this collection. Find any two irrational numbers between 1 by 5 and 2 by 7. 1 by 5 is this, 2 by 7 is this. To find two irrational numbers between 1 by 5 and 2 by 7, we need to look at the decimal form of the two numbers and then proceed. We can find infinitely many irrational numbers such as like this 0.20, 120, 1120, 111. Okay, without any pattern. If it is repeating, then it is irrational. Can you find more irrational numbers between 1 by 5 and 2 by 7? Definitely you can find an irrational numbers between 3 and 5, 3 and 4. Just multiply both. Okay, 3 into 4 is 12. Make a root. Okay, that is 2 root 3. Okay, root 12. If the product AB is not a perfect root, then root AB becomes the irrational number root AB lying between numbers A and B. Examine whether the following numbers are rational or irrational. This is rational number. This is also rational number. 9 minus 3, 6. This one is 6. And what about this? Root 5. So irrational. What about this? This is also irrational. Okay. Rational. Rational. Irrational. Irrational. That is what I mentioned, right? Classify the following numbers as rational and irrational. Root 27 or 3 root 3. So irrational. Root 441 irrational, not a perfect square. This number is going like without any repetition. So this is irrational. This is rational. Okay, repeating. This one is not repeating. So irrational. Right. Right. This one is repeating, no, not repeating, so irrational. Give the examples for rational irrational number that you can give. Find a rational number between 5 by 7 and 7 by 9. How many more there may be? Many more. To find two irrational number between 0.7 and 0.77, that also you can do. Find the value of root 5 up to 3 decimal places. How to find? You can do the continuous division process, long division method. Okay, root 7 also up to 6. Okay, we'll do it for root 7. Okay, this is the setup, right? Fine. So here 7, this is 7, so you have to take same numbers, right? 2 2 is a 4, 3 3 is a 9. 9 will be more, so we have to take only 2. So we can take 2 2, so 4. So 4 will come here. 7 minus 4 is how much? Yes, 3. Okay, 3. Okay, so 2 plus 2 is 4. So we have to proceed with 4 here. Which is more? 4 is more than 3. So we need to put a point here. Okay, then we can take 2 or 1. 2 zeros. You can take 2 zeros since you put dot there. Okay, 300. Now you can experiment, you can try with 5. 5 5 is 25, 2, 5 4 is 20, 22, 6, 6 6 is 36, 3, 6 4 is 24 plus 3, 27. 6 is sufficient. 7 will be more, I think. Yes, 6 only. So here 6 only is suitable. 6 6 is 36, 6 3, 6 4 is 24, 27, 276. All right, 276. If you subtract 276 from 300, how much you will get? 14. Right, 14 only. No, 24. Right, 24 only. So now you add 46 plus 6, that will be 52. Okay, so 52. Yeah, already we kept that dot is there, means you can take 2 zeros because 24 is less than 52. Okay, now you can try with 2. 2 is smaller number. 3 perhaps. 3 3 is a 9. 3 2 is a 18. 1 3 55 is a 15 16. 4 maybe perhaps 4. 504 is a 2000 maybe 4 is okay. 4 4 is a 16 1. 4 2 is a 8 9. 4 5 is a 20. Yeah, 4 is okay. 5 is more I guess. So we will take only 4. Okay. The number will be 4 4 is 16 1. 4 2 is 8 9. 4 5 is 20 2096. Okay. Fine. How much this is going to be? 4 last digit, before that 0, 9 minus 9 0, this will be 3. Okay, no, not 3, 2, no, 3 only, 3. Okay, yeah, 3 only. 524 plus 4 528. Again 528 is more than the number here. Okay, but we can put 2 zeros anyway, because we already did something to put a dot here, right? So again you can proceed it like this. Which number is suitable? 2 is suitable. 2 2 is 4, 2 8 is 16, 1, 2 2 is 4 5, 2 5 is 10. 2 is little, then maybe perhaps 4. Okay, let's work on 4. 5 also suitable. 5 5 is 25. I think 5 is also suitable. 6 is more, I guess. Okay, 5. 5 5 is 25. 5 8 8 is 40. 2 4. 5 2 is 10. 4 1. 5 5 is 25 26. Yeah, 5 is okay, no problem. Now multiply it with 5. 5 5 is 25. 5 2. 5 8 is 40. 2 4. 5 2 is 10. 4 1. 5 5 is 25 26. Okay, this is the number you will get. Okay, then on subtraction, last digit will be 5. Okay, I am okay with 5. 9 minus 2 is 7. 13, yes, 13. 13 minus 4 is 9. 9 minus 6 is 3. So this is going to be 3975. Okay, right, that is quite correct. How many decimal places he told? 6 decimal places. See the problem. How many decimal places he wants? So root 7 up to 6 decimal places. Okay, how many decimal places we got? We got only 3. Okay, let's proceed from here. 5290. Okay, here this is less, put 2 zeros. Okay, right. Getting bigger, right? 4, no, 5, 5, no, 6, yes, 6, 7, yes, 7 also you can try. You can try with 7. 8 will be larger, that is for sure. 7 we can try. We will try with 7. 7 7 is 49, 7 9 is 63, 6, 7 2 is 14, 6 22, 7 5 is 35. Yeah, perfectly all right. So proceed with 7. What is here? 7 7 is 49, so 49. 7 9 is 63, 3, sorry, 3, 6 will be there. 7 2 is 14, 14 plus 6 0 2, 7 5 is 35, 37. Okay, let's now subtract. After subtraction, what will you get? Last digit will be 1. Okay, before that 5. Fine. 4 minus 3 1. Okay, 7 minus 0 7. 5, fair enough. 9 minus 2, 9 minus 7 2. Okay, right. 27151. Now you add 7 to this number. What will you get? 14. Yes, 14. Now this is smaller than this. Again you have to get 2 zeros. Okay, add 2 zeros here. Okay, which number? This is 27 here. 5 will be larger. 4, I think 4 is okay. I think 4 is okay. 4 5 is 20. 5 5 is 25. Why not 5? Why not 5? That is also a good question. 53 into 5. 53 5 is a 5, I guess, is fine. Okay, we'll try with 5. If 5 is not suitable, we will go back to 4. 5 5 is 25 2. 5 4 is 22 2. 5 1 is 5 7. 5 9 is 45. 5 4. 5 2 is 10 4 1. Yeah, 5 is okay. Perfectly alright. Okay, then the first digit will be 5. 2, 5 4 is 22 2. 5 1 is 5 7. 5 9 is 45. 5 4. 5 2 is 10 4 1. 5 5 is 25 26. Okay, so this is the number. Okay, now okay, um, so how many digits we got so far? We got almost 5 digits, right? 5 decimal places. We need to get one more. Okay, so surprisingly this number starts with 2. See, second number is 6, third is 4, fourth is 5. Okay, fifth is 7. Almost 5 digits are matching, right? Okay, leave it aside. Now subtract this from this. What you will get? We are only one step lagging behind the final answer. 10 minus 5 5. 9. Oh 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 oh. Wait a minute. Okay. 10 minus 5 5. 9 minus 2 7. Right. 10 minus 7 3. Fine. 19 minus 5. No, 9 minus 5. 4. Okay. No, sorry. 14 minus 5. 9. Okay. Then 10 minus. Oh. 10 minus 4. 6. That's it. Okay. 69375. Now you need to add 5 to this, so this becomes 50. Right. Now which one is more? 5 digits, 6 digits. This is more, so add 2 zeros as usual. Now see the last digit. Okay, 5 Mm-hmm. 529 19150. If I place 1 here, 529 1501. Okay, one only, maybe that will take only one, I guess, because if I take two, this will be doubled, right? So how many digits are there? 3367. Here 3367. No, one only will do the job. Okay. Uh-huh. We need to cross check whether we are right. Our assumption is, I suppose it is right, but still we need to, better to cross check, right? Mm-hmm. uh, 10 minus 1 9. This is also 9. 14 minus 5 9. 6 minus 1 4. Mm-hmm. 13 minus 9 mm, 6. 13 minus 9 4. Okay, 4. 9 minus 2 7. 6 minus 1 6 minus 5 1. Okay, so that is almost 7 digit number starts with 1. 1 2 3 4 5 6 7. Okay, less than this only. So this is the final answer, 2.645751. 7 root 7 with those many digits. How many digits? 6 digits. Okay, fair enough. Locate root 10 on the number line, that you can do. Find at least, see, this is 3. Okay, after 3 only you have to extend 1 centimeter. Okay, perpendicularly, that is vertically. Then you can add the origin point and the final point of this 1 centimeter. Okay, that is root 10. Okay, find at least two irrational numbers between 2 and 3, that also you can do. State whether the following statements are true or false, justify your answer. Every rational number is a, every irrational number is a real number, right? Every rational number is a real number, that is also right. Okay, these two are subsets of real numbers. Every real number need not be a rational number. You're right, that can be irrational also, that is also correct. Root n is not irrational if n is perfect square. Right, that this is correct. Root n is irrational if n is not a perfect square, that is also correct. Okay, all real numbers are irrational, this is only false. Sixth one is false. Okay, activity constructing square root spiral. Okay, this is exercise 1.1, 1.2. Okay, we'll stop it here at exercise 1.2. We'll continue the remaining in the next session. Okay, thank you. Are you tired of dental problems? Then listen to this. Stop brushing your teeth using plastic brush and chemical paste. Use nature's gifted neem stick for brushing your teeth and stay healthy.